Hello everyone, in this video we provide a simple and easy to understand introduction to recurrent neural networks in Keras and TensorFlow. This video tutorial is organized as follows. First, we provide a brief introduction to equations governing the behavior of recurrent neural networks. Then, we proceed by explaining the structure of recurrent neural networks. For example, we will explain the unfolding process in time, and finally, we will focus on a practical example. The main purpose of the practical example is to explain you how to use recurrent neural networks to predict future samples of time series. The idea is to use the past samples of time series to create a predictor that will predict the future samples. In this video, you will learn how to solve this practical problem by using TensorFlow and Keras Python's library. Furthermore, I have created a post that nicely summarizes everything that I will explain in this video. This post contains theory, contains graph, contains a thorough explanation of all the Python codes. Furthermore, all the codes are posted on my GitHub page and all the links are provided in the description below. In order to better explain you the main ideas behind the recurrent neural networks, we will use one simple form of a recurrent neural network. These two equations describe the behavior of the so-called simple recurrent neural network. For those of you who are familiar with control theory, you will immediately recognize that this is nothing less than a state space model. The first equation is the state equation, and the second equation is the output equation. The state equation tells us how the states of the system are propagated in discrete time. Here, hk-1 corresponds to the state of the system at the discrete time sample k-1. Similarly, hk corresponds to the state of the system at discrete time sample k. Okay, let us explain other terms in this equation. Alpha h is a nonlinear function or the activation function that acts on this sum over here. Then a, b, and lowercase bh are network parameters that we want to learn or that we want to train by using the input and output data. Then the next term is basically UK. UK represents the input to the recurrent neural network at the discrete time k. So if I know the model parameters a, b, and lowercase bh, and if I know the input to the network at the time sample k, and if I know the state of the network at the time sample k-1, that is, if I know h k-1, I can simply propagate this equation to compute the state of the network at the time instant or time sample k. That is, I can compute h of k. The second equation is the so-called output equation. This equation maps the state at this time sample k to the output of my recurrent network at the same time sample k. Alpha y is a nonlinear activation function. C and B are model parameters that we learn from the data, that is, that we learn while training the network. And this equation, together with the state equation, governs the behavior of my recurrent neural network. Next, we explain the unfolding process in time. Let us assume that we know the state of the network at the time sample 0. That is, we know h of 0. And let us assume that we know the inputs to the network at the time samples 1, 2, 3, 4. 4 is enough. That is, we assume that we know u1, u2, U3, U4. Then, knowing the model parameters A, B, and all the biases, B, H, and By, together with the matrix C, we can simply propagate our state and output equations to compute the outputs and future states of the network. So we start from H0, we know the inputs, we propagate this equation to compute H1. Then, knowing H1, we can propagate the output equation to compute the output. Then we repeat this process. Now, since we know H1, we can substitute it over here, and recursively we can compute H2. Of course, assuming that U2 is known, then we can from H2 compute Y2. Then we can use the previous value of H2 and propagate this value in time, again knowing the input, to compute H3. Then from H3 we compute Y3. Then again we use H3 to compute H4, knowing the inputs, the input at the time sample 4, and then again knowing H4 we can simply compute Y4. So this process, the unfolding process, will produce H1, H2, H3, and H4. And from the output equations, we can simply compute the network outputs Y1, Y2, Y3, and Y4. This flow of information can be illustrated by this figure. That is, knowing H0 and knowing all the inputs, we can compute H1, H2, H3, and H4, as well as all the outputs, by simply propagating the state and the output equations. In order to make this video as brief as possible, we are not going to explain in more details how to train a neural network or how to perform backpropagation in time. The equations might be too complex for someone who is a total beginner. Instead, we will explain you how to use recurrent neural networks to solve practical problems. And here is the illustration of the problem that we will consider in this tutorial. The problem is to predict future values of time series from past measurements. My horizontal axis is time, and my vertical axis represents the values of time series. These red crosses represents samples of my time series. Now, if this is the present time, my goal is to predict the future values of my time series, knowing the past values of the time series that are given over here. This is a typical prediction problem, not only for time series but also for dynamical systems, because you can think of Q of K as an output of a dynamical system, and the problem is to predict the future behavior of your dynamical system knowing the past measurements. In order to predict the time series, we need to train the model. However, to train the model, we need to have the training data. This means that we need to record the original time series over a certain time interval, and we will use these samples to train our recurrent neural networks. However, the story does not end at just recording the data. It's very important to properly organize our data into input and output data sets. And in the sequel, we will explain how to properly organize and form these data sets. We form the input and output data sets for training the neural network by splitting the original time series into a number of subsets. We form the first subset by cutting the time series over here. And we use all the samples starting from the beginning of time series until the point over here to form the first subset. And for illustration purposes, the first subset is represented over here. The next step is to split the first subset into two parts, the black part and the red part. Basically, the black part is used to predict the red part, and consequently, the samples corresponding to the black part, the samples starting from here and ending up here, will be placed in the first row of the input data set. That is, they will belong to the first row of the input data matrix that is called data set X. Consequently, the red samples, or the samples corresponding to the red part, will be placed in the first row of the data set Y that represents the output matrix. By using this data partitioning, we will tell to our neural network to predict the red samples on the basis of the black samples. That is, predict the first row of the output matrix by using the first row of the input matrix. Let's see how to form the second subset. Well, we will simply offset our time series and we will form the second subset by taking the samples from here until here. And this subset is represented over here. Then again, we split this subset into two parts, the black part and the red part. Then again, we take the samples belonging to the black part and we place them over here. That is, we fill in the second row of the input data set by using these entries, and similarly, we use the red samples and place them in the second row of the output data matrix. Similarly, we form the third subset and all other subset by again offsetting our original time series and making additional cuts. For example, the third subset is formed by taking samples from here until here, and the third subset is represented over here. Again, black samples go into the third row of the input data set and the red samples go into the third row of the output data set. And by repeating this procedure, we can populate our input data matrix and our output data matrix. Here is the Python code for training the neural network and for evaluating the neural network performance. First, we import the necessary libraries. We import the NumPy library, then we import the plotting tools from matplotlib, then we import TensorFlow, then we import Keras, and finally we import from keras.callbacks model checkpoint. This function will be used to save the model with the best parameters. We should emphasize that best parameters are the parameters that produce the smallest validation error during the training. In this way, by tracking the validation error, we can basically ensure that the model is not overfitting and that the saved parameters or the trained parameters correspond to the model that performed best on the validation data set. The next step is to define the time series and model parameters. In this video, we will use an artificially constructed time series. However, everything that will be explained in this video can be generalized to real-life time series, such as time series of stocks or time series of physical processes, such as temperature change or pressure change. First, we construct the time series and model parameters. The first parameter is time steps. In our case, it's equal to 5,000. So we will construct a time series whose length is equal to time steps. It will have time steps parameters. The next model parameter is the batch size. In our case, it will be 200. The batch size parameter corresponds to the number of rows of input and output data matrices. The next parameter is the offset parameter. It's equal to 5. Here is the offset parameter. It's basically time offset between two subsets. The next parameter is the length. This parameter corresponds to number of columns of the input data set, that is, the number of columns of the input matrix. Now, this parameter is actually equal to the number of samples corresponding to the black region of the data subset. So we will use length samples to predict future samples. The next parameter is the prediction horizon. The prediction horizon is equal to the number of columns in the data set Y matrix, that is, the number of columns in the output data matrix. The prediction horizon is equal to the number of samples in the red part of the time series subset. So generally speaking, we are using the length number of samples to predict prediction horizon number of samples. The next step is to construct empty input and output data matrices. My input data matrix is called dataset X and the output data matrix is called dataset Y. Then the next step is to construct our time series. In this video, I'm assuming that the time series is equal to the sum of harmonic functions. Harmonic functions are sinus, cosinus functions, or some combination of sinus and cosinus functions. So here is how I construct my time series, and let us plot the time series. So here is my time series. I'm only plotting first 100 samples. Basically, the next step is to populate input and output data matrices. As explained previously, we are splitting the original time series into subsets, and then we are populating input and output matrices row-wise, where we are offsetting the subsets. And basically, this is what is happening in this for loop. You can see an offset parameter, you can see prediction horizon, length, and other parameters. Now, once we have formed these matrices, we need to reshape them, since if you just define them like this, let me just execute this once more, you'll see that the shapes of dataset X and dataset Y are as follows. Now, if you provide these inputs and outputs to the recurrent neural network implemented in Keras, you will receive an error. Basically, the dataset should have an additional dimension, should be tensors, should have an additional dimension, and this dimension will be a single dimension. So this is why I am executing these two code lines to reshape these matrices. Once you reshape these matrices, you will have the following dimensions. And now these matrices, or better to say tensors, can be plugged into the Keras recurrent neural networks. Next, we split the original input and output data sets into three subsets. We split the original data sets into the train, validation, and test subsets. The train and validation subsets are used during the network training. The training subset is used to train the model parameter. The validation subset is used to validate the performance of the network during the training, and the final subset, that is the test subset, is used to validate the final performance of the network once all the model parameters have been trained. So let's create these subsets, and the next step is create the model. We create a sequential model consisting of three layers. The first two layers will be GRU layers, or gated recurrent unit layers, and the final layer will be a dense layer. So gated recurrent units are a type of recurrent neural networks whose structure resembles the structure of simple neural networks. However, they have a few additions that I will not discuss in this video in order to make this video as simple as possible. You can read more about GRUs, for example, on Wikipedia or by opening Keras documentation. So I'm having these two networks. I'm assuming that the first network is returning all the sequences. Okay, let's discuss this parameter, return sequences true, in more details. So let's see what's happening. Basically, once you define a neural network or recurrent neural network, you have two options. The first option you can see over here. Basically, the first option is to return the output corresponding only to the last sample. And you obtain that option by specifying here return sequences false. However, I don't want that. Instead, I want my network to have the following structure. So I want to return the output sequence at every time step. So I'm assuming that the first layer has this structure. Now, let's look at the second layer. The second layer has a similar structure. However, here I'm assuming that return sequences are false. So I'm assuming this structure. So you can visualize these two layers as this part over here connected with this part, where these outputs become inputs for the second layer. So this is the first layer. Its outputs become inputs to the second layer, and the second layer basically spits only single output. And then this single output is connected basically to a dense layer, where the total number of outputs of a dense layer corresponds basically to the number of neurons and is equal to prediction horizon. Remember that the number of rows in my output data set is also equal to the prediction horizon. Or better, I need to correct myself, the number of columns in my output data set corresponds to prediction horizon. Here, another thing to notice is that I'm assuming no bias, so I'm assuming that there is no bias parameter in the system. If you go back to our original equations, I'm assuming that I don't have this term here and this term here. They're set to 0. And another thing to notice is that I'm assuming a linear activation. Basically, linear activation means that alpha h and alpha y are equal to 1. Then here I specify the input shape. I specify none, 1. Basically, none can basically handle input sequences of general lengths. So I specify none. However, you can also specify, for example, length. And the length is the parameter given over here, defined over here. Okay, so once I create my model, let's see the model. Okay, I can create basically a checkpoint. So what is a checkpoint? Basically, a checkpoint is a function that's used to save the model parameters during model training. So here what I'm basically doing, I'm saving in this folder my model parameters. So let's see that folder. So the models will be saved over here, and the model parameters will be saved exactly in this file. So if you see over here, there is a path, it's codes, recursive, saved models, weights. Basically, this is the path to this file, and this is a specific HDF5 extension that you need to use in order to save model parameters. So in the model checkpoint function, I specify the file path, I specify what I'm monitoring. In this case, I'm monitoring validation loss. Then verbose is just a parameter, and here I specify the parameter save best only true. That is, I'm only saving model parameters that produce the most optimal validation loss. And then here I specify save weights only false. That is, I'm not only saving weights, I'm saving everything, and the mode is auto. You can read more about these other parameters in Keras documentation. Once I create my model checkpoint, I can basically compile my model by specifying the loss. The loss will be mean squared error. The optimizer will be Adam, and the metrics for tracking will be mean square error. I can do that, and then I can do model summary. So here is my model summary. I have basically 3 layers. These are the output shapes of every layer, and these are the number of parameters. So I have 360 parameters. This is a relatively large number of parameters for basically learning a simple function, but never mind. This video is made only for illustration purposes. Okay, so let us fit the model. I specify here in the model.fit function train values, right? Input and output train data. I specify the batch size. I specify the number of epochs. In this case, I will use 5,000 epochs. And I specify validation data. Then I specify here callbacks. Callbacks will correspond to my model checkpoint, right? And let's execute and let's start training the model. Okay, so now model training is basically happening. I'm seeing here my loss and I'm seeing my validation loss, right? So you can see the training loss, these two values over here, loss and MSE, these two first values or the values corresponding to first columns are training loss, and the validation loss corresponds to columns number 3 and columns number 4. So after approximately 5 minutes, the training process is completed, and the next step is to load the model weights. I'm loading the model weights that produce the lowest validation error that is calculated during the training. The next step is to calculate the model prediction. Basically, we want to verify the model performance. For that purpose, I'm using the input data set from the test data set. So these inputs are never seen during the training process. That is, the network is not using X-test during the training process. So let's calculate the prediction. The next step is to check the validation and training curves. So this is my training loss, the blue line, and the red line is my validation loss. And I cannot observe overfitting since the validation loss follows the training loss. I can achieve maybe even better performance by increasing the number of epochs from 5,000 to, let's say, 10,000. Okay, so let's visualize the prediction and test data. So what do? I take the first row from the prediction data set and I compare that rows with the first row from my output data set from the test data set. So let's see what's happening. I see a very good match. So my network is able to accurately predict the output from the test data set. This is really encouraging. So I'm able actually to predict future time series relatively accurately. Let's check the second row from the prediction data set. Remember that the second row is just basically a shifted version of the first row plus additional terms that are not in the first row. So let's verify the performance and let's see what happens. Okay, not bad, not bad. We see a relatively good prediction after, for example, 3 data samples. Okay, that would be all for today. I hope that you like this video. If you like the videos I create, please subscribe or support my channel. Thank you very much and have a nice day.